Hello everyone, we welcome you to the introductory video on our MOOCs course on optimization techniques for digital VLSI design. As you see, this course will be delivered by Dr. Chandan Karfa and myself from IIT Guwahati, and it will be a 8-week duration course. As we all know, what is digital design? Basically, it is a course which is taught in all UG curriculum in the second year. But whenever we talk about digital design and slightly advanced version, we call it actually a very large scale integration system. So how it basically works? So if you see the basic flow, we start with the customer requirements, that what we want to design. It can be as simple as like two adders where you will add two numbers like A plus B and C plus D, or it can be as complex as an automatic cruise control system of an advanced network on chips and network processors. Then what we do, then we go for some architecture level synthesis, because our specifications are simple abstract mathematical operations, or they can be some algorithms. Then we go for a high level synthesis, in which case we decide whether you have to use an adder or whether you have to use a multiplier, or how it will look like in terms of several block level design. So in this case, as you can see, I have taken a very simple case. We require two adders to produce out 1 and out 2. Then what we do, finally, as it's a digital design, whether it's a VLSI or it's an ultra large scale integration, after all, basically they are all digital designs. Mostly we are talking about digital design in this course, and we are not talking about analog and mixed signal, which is not a part of this course paradigm. So we'll be mainly concerned in this course with digital circuits. So finally, second level, you will have to have a circuit which will actually implement the architecture design into gate level implementation. Like in this case, it's a sum and a carry. Then you have to finally lay it out in terms of transistors, because that is what is exactly going to be fabricated. So this is actually called a typical VLSI design flow. But you have to also note that we have to verify that whatever was our intent is exactly being realized in silicon or not. So you can find at every point there are some verification steps. That is, they find the equivalence between our specification to RTL, RTL to gate level, and finally from the gate level to the transistor level. So after design, we go for formal verification, that whether these steps are proper or not. So if you look at in this case, here the verification will be very trivial, because we are just going to add two numbers. But you can understand the complexity when you are designing a processor or when you are designing a mission critical systems like a cruise control in a missile. Then finally there is something called test, because whatever we fabricate in VLSI or in digital design may have some manufacturing defects. So in this case, we take a circuit. Before that, we go for a test plan. Then we fabricate it, and then finally we apply some test patterns to see whether the output is proper or not. So in this case, that is a simple adder. I assume to be a half adder. So basically you have to apply all possible inputs. So this is basically a typical VLSI test flow, or you call it the digital design test flow. It doesn't matter much as long as your specifications are as simple as that. But whenever I basically change it to a processor, to a system on chip or a network on chip, you can see the simple layout we just looked as a single transistor will now translate to a millions and trillions of transistors when it goes for a AMD processor, Intel processor, or a network on chip or a system on chip. So what exactly will change when you go for a simple digital adder to a as complex network of systems or a network of processors, etc. So therefore, in such case, all these steps of design, like taking a specification, convert it into a high level synthesis, converting it into a RTL design, then to a gate level, and finally laying it out, and even testing and verification, nothing can be done manually. You will have to have some CAD tools to do that. So that is a subject which actually all of us might have heard of, which is called the CAD for VLSI. But if you look at the CAD for VLSI perspective, so whenever we basically look at this actually discusses that we started with tens of transistors when it is a small scale design, when it was a simple calculator or a simple logic circuit. Then we went for medium scale integration, and now basically we have always hear the term called very large scale integrations with thousands and lakhs of transistors. So whenever we go for very large scale integration, the CAD tools are very much required. So we start our design maybe with a Verilog or a HDL language. Then we have high level synthesis tools which will give you an RTL design. Then you have RTL synthesis tools. Then we have automatic verification tools like spin. And if you are going for industry level tools, we have tools from Cadence and Opsus. And finally we have to go for testing, and tools are available to generate test pattern called Tetramax. in a traditional industrial environment, and also their academic counterparts. But nowadays actually in this course we'll be mainly thinking of ultra large scale integration systems, or a network of chips or systems of chips, which is again much larger in terms of complexity compared to a normal VLSI design. So VLSI you can think of a single processor, but when you have a network of processors where there are 128 cores with some hundreds of memory banks with L1, L2 caches, even the CAD for VLSI flow will have to be modified to handle the complexity of such a large level where it's a system of systems. So this course basically will tell you what modifications you have to do, or what optimization steps you have to inbuilt or you have to get into the normal CAD flow, so that we can use the CAD flow to design such advanced or high level or very complex system of systems like NOCs and SOCs. Okay. So now my partner Dr. Chandan will tell you about our course plan and what we are expecting out of it.
So in this course will go along with this CAD flow. So we'll talk about high level synthesis, logic synthesis, physical synthesis, testing and verification briefly. But as you mentioned, the focus is on the optimization and the keeping it more abstract level. So if you just think about this high level synthesis, if you just see high level synthesis, steps are like scheduling, allocation, binding, data path controller generation, right? So we'll briefly cover that obviously, but what we're going to cover or going to give more emphasis here is like how, we'll start how we can use high level synthesis effectively. It means suppose you start high level synthesis from a C code. What would be your C code, right? What is the good way of writing C code so that the kind of generated hardware, the hardware that we're going to generate out of it will be efficient in terms of timing and power or area, right? So it's not that all C will give you the same hardware. So you have to know which is a good C, right? So writing your C, the way of writing C is important. So you try to emphasize on that part. Similarly, if you just make it abstract to C level, now all the compiler optimization that you taught in compiler courses come into picture, right? We'll also talk about those compiler optimizations, how they're going to impact in hardware. You just think about loop transformations like loop unrolling, loop tiling and etc., code motions. So if you just think about those techniques, how they are going to impact in your hardware. So we are going to discuss more on those aspects of high level synthesis, right? So in the module 2 we'll discuss definitely on logic synthesis and physical synthesis. We'll discuss about 2-level optimization, multi-level optimizations, heuristic optimization like espresso. We'll talk about physical synthesis steps like placement, floor planning, routing, those things briefly. But what we're going to discuss more on basically, if you just FPGA prototyping, right? If you, as you mentioned, when you design a big processor, first it is as prototyped in FPGA, check whether these things are working for say a week or so, and then it's go for final fabrication ASIC, right? So we'll just talk about what is FPGA's prototyping, how difficult it is, right? And also if you just think about the FPGA, so FPGA has a lot of dedicated blocks like DSPs, RAMs and all. So how to utilize these things, right? How to write your C code so that effectively that will be mapped, that will infer more DSPs and RAMs in FPGA synthesis, right? Or how to write your RTL, how to change your RTL. So your minor change might infer more DSPs and RAM, right? So we are going to discuss about those aspects here clearly. And we have also a very dedicated module 3 just to discuss about the RTL optimizations. As you know, the RTL is kind of still the starting point of any digital designs. So we'll just talk about all the optimizations that are used for area, timing and power, specifically area and timing and power, because these are more important factor nowadays. So what are the techniques like retiming, register balancing, folding, pipelining, replication, clock getting. So we'll discuss all those techniques, how they're going to impact in hardware generation, so that it will give a very clear idea that how to use those techniques, right? So the other two parties on testing and verification that will be covered by Dr. Vishwa, so you can highlight that.
So in VLSI testing, even in the very VLSI era, you do not generate all patterns. Like you don't go for a functional testing, you go for structural testing, in which case we might have read about some stacked fault models and some well-defined fault models which work at the gate level. But as my friend mentioned, that in this course now if we are going for an ultra high scale integration or very complex system, we start with C type of programming language. So our fault models will no longer be at the logic level, because if it is so, it will blow up the complexity. So we have to go for high level fault models, we have to go for testing at the C level, and we have to, which is called the RTL level test. We will test at the RTL level, but actually the test should be reflected at the gate level. So all such ways of modifying or optimizing the test so that it works for a system which is described in C or a very high level language can be accomplished. So our test part will be highlighting on that. Of course, we will give you the basics on what is the paradigm of test from a traditional view, but we will more emphasize on what has to be changed if you are going for testing of very complex systems. Another important perspective is that here we do not always target 100% coverage. We can slightly compromise on this because the system is so high so that we can achieve something which is tangible financially within a given amount of time. Then I will go for verification. Same like testing, verification means you have to mathematically prove that everything is satisfying your intent. But again, I cannot do a full 100% or full intent verification using the traditional flow which is done in case of VLSI or small systems. So we will go for some abstract type of modeling and slightly compromised type of verification, like instead of binary decision diagrams, we will be using arithmetic decision diagrams or high level decision diagrams. We will be using symbolic model checking and bounded model checking kind of techniques, which may slightly compromise on your basically the amount of coverage you are getting, but you can achieve the desired intent in a smaller amount of time, which is the need of the hour because your systems are so large. So with this 5 modules, we will basically try to cover how very advanced systems can be dealt with using a traditional CAD flow. What are the modifications required?
So who should attend this course, right? So students who want to work in the VLSI design and also in the electronic design automation flow, and professionals who work in the industry in these areas, it will be very useful course for them, because as I mentioned earlier, the course is not only just targeting the CAD flow, it's targeting the 2 important key factor to make it scalable, right? So just we will talk about the abstraction and optimization. So this kind of techniques is will be discussed on detail, so it will be very useful for people or professionals who want to work in this area, right? Now the question is why this course you should attend this course, right? How this course is unique compared to others. But to be honest, there are many such courses in CAD for VLSI available online, right? So but this course targets is little bit different. It's not targeting the normal CAD flow, as I mentioned again. It's basically targeting 2 other important aspects, these abstractions and this optimization. So we try to discuss all those things in more detail, and that will give you a very comprehensive idea about those techniques. And people who want to work in the design, they can use those techniques when they're designing some RTLs, or people that are working in the EDA flow, they can also think about implementing those things in the CAD flow so that their tool can become more sophisticated, right? So this course will be useful for both of them. I hope this course will be very useful for people who are going to attend. I hope all of you are going to attend this course, and it will be an enjoyable journey for 8 weeks for both of us. Thank you.
Thank you.